Okay, so why don't we go over, continue with the nomenclature. Now, last week we talked about covalent or molecular naming. For example, we had something like water. Okay, so water is going to be molecularly named or covalently named. Now, how do you know it's covalent or molecular? To be an ion, you have to have a cation and an anion present. Okay, so a cation, remember, is positive and anion is negatively charged. My dog wants to go out. Too bad. Um, and water is not that. Water is, if you look up oxygen, which is an oxide, it's a -2, and hydrogen is a -1. So it's got two negatives, not a positive and a negative. So it's considered molecular. And yes, I will provide this common ion chart for the test. Okay, so to name that, it always has two parts. Let's see, I'm going to make small. Maybe not. Okay, it's always got two parts. This is from the periodic table. And the second one is an ide. So H from the periodic table is hydrogen. And the ide for oxygen is oxide. So now we have to say how many of each we have. Well, we have two hydrogens. That's the same as di right here. And we have one oxygen, so that's going to be a mono oxide. Now notice I didn't write the second O. If you've got two vowels together, you can drop the first one. So instead of MONOOXIDE, it's just MONOXIDE. And you'd pronounce it as monoxide. So it's dihydrogen monoxide. Okay, the dry lab for today and tomorrow has you practicing naming this stuff, where I give you the formula and you tell me the name, or I give you the name and you write the formula. So let me do another one on the molecular side where I give you the name and you write the formula. Okay, so let's say we had penta, um, pentachlorodihydride. Okay, that should be actually Why doesn't that move over? All right, from the periodic table, and I forgot what they had the second one. Dihydride. Okay, so penta is 5, chloride is Cl5, hydride is hydrogen, and there's two of them. So you need to go from formula to name and name to formula. This is a matter of just practicing it. Okay. Oh, and by the way, I have an alternate Dry Lab 5 for you to do. That's much clearer, in my opinion, than the one in your lab packet. So that's the one we're going to do. It's on files, lab related. It's lab 05, and you'll see it there. Okay. Um, all right, so let's go into the ionic now. Now there's some teachers teach this slightly different. They'll say cation and anion, or they'll say metal and non-metal. They're one and the same. Metals are all positive, non-metals are all negatives. 6 of one, half dozen of the other, depending on what textbook you're reading, what teacher you're hearing this from. Both of those are valid in my class, however. Okay, so the thing about ionics, you have to have a net zero charge. That means the number of positives equals the number of negatives. Let me give you an example. Let's see, let's not do that. Let's do sodium sulfate. That's an E, by the way. Sodium sulfate. So if we look up, yeah, someone have a question? All right, so let's look up sodium sulfate. Okay, so where would that be? Sodium sulfate is positive, so it's on the left. We go down to sodium, and that's a +1 right here. +1. You could write it like that or like this, either way. 1 plus or just plain old plus. All right. Sulfate is SO4. And what charge is that? Because it's negative, it's going to be on the right. It's right here. and that's got a charge of -2. Now, +1 is not equal, does not negate a -2. Only a +2 is going to negate a -2. So that means we need 2 of these to balance the SO4. 2 of them will give us a +2 against the -2. So sodium sulfate looks like this without the charges. So the charges are there just so that you balance out the charges. So you end up with a net 0 charge. Does that make sense?
I think I might have to go back and rewatch it a couple times just to like let it like parts of it make sense, but to really completely understand.
Yeah, no, I totally understand. This is the first time you've seen it, right? Okay, so let's do some more here. Let's do calcium hydroxide. It's a very common chemical. Um, so let's look this up. First of all, is it covalent or is it ionic? Well, calcium is a +2. Hydroxide is a -1, and it's a group, so that needs parentheses. Okay, so we've got a cation and an anion, or a metal and a nonmetal. So it's ionic. That means we have to do charge balancing. Okay, so calcium actually is a +2, not +1. Calcium is a +2, hydroxide is a -1. So that means that they're not balanced yet. So we need 2 negatives to balance the +2. So that means we're going to have 2 of these right here. Now we have -2 against the +2. So to write that without charges, that's the formula for calcium hydroxide. Now I want to show you something peculiar about metals. Sometimes a metal can have multiple charges. For example, lead. Lead has got a +2 and a +4. So which one do you use? Iron, +2 and +3. Which one do you use? Copper, +1, +2. Which one do you use? Okay, notice the ones that have multiple charges have a parentheses with a Roman numeral in it. 1, 2, 3, 4, 5, 6, whatever. That denotes the charge. So this is a +1 charge, +1 charge, +2 charge, +2 charge, etc. So when we name it, we've got to figure out which one is appropriate to use. And also, sometimes there are multiple names of the same thing. For example, copper 1 is also called cuprous. Copper 2 is called cupric. Now, these are the old names, and excuse me, the industry has not chosen to not use the new names, the ones with parentheses. It uses the old names. Okay, that's the pharmaceutical industry, the ag industry, the food industry. If you look on a food label, you're not going to see copper one, you're going to see cuprous. You're not going to see iron two, you're going to see ferrous. Ferric, for example, ferric oxide, also known as rust. You don't see iron three oxide, you see ferric oxide. So I always like to give you both names so you have reference to both. Chemists like to use the parentheses because they're the ones who invented this. Um, Biochemists depends. Some of them do, some of them don't. Um, Biologists don't at all. Most of them are the old names: cuprous, cupric, ferrous, ferric, etc. Okay, so that's why there's multiple ions. That's why there are multiple ions with different charges. And it has to do with the way the electrons are situated inside around the nucleus. There are various versions that are stable. That's why you get multiple forms of iron, for example. The positive two is stable, and so is the positive three. You'll see more positive twos than positive threes because the ferrous is a little more stable, but still. But there are also Fe plus ones, plus fours, plus five. It's just that those are not the common ones. These two are the most common. Copper one, copper two, those are the most common. Okay, so that's what that's about. So let's do some more of this now. And if you look at calcium, calcium only has one state. It's always a plus two, nothing else. When we get into electronic configuration, I'm going to show you why it's got a plus two only. Okay, now I mentioned a couple things here. The SO4 is also a group. So normally if there's more than one in the group, you put parentheses. I encourage you to put parentheses anyway, even though there's just one there. That denotes that that's a group of molecules, or excuse me, of atoms that make up a minus two charge. Now, tomorrow we're going to talk about Lewis dot structures, which will actually show these, what the electrons are doing around here. Okay, so let's do some more examples. Now, all I'm going to do now, they're all going to be ionic, but you need to figure out first whether it's molecular or ionic or covalent and ionic, using the test where we have a cation and an anion. Um, let's see now here. Sodium phosphate. What's the formula for that? Okay, if we look up here, sodium is going to be, cations are on the left. Go down to sodium. Sodium is Na plus 1. Phosphate is over here, and it is a minus 3, if I can find it. Where is it? It is right here. PO4 minus 3. So we have a minus 3 and a positive 1. Okay, so sodium, +1, phosphate, -3. Now again, you can write this 3 negative or -3. Back in 1964, when I was in high school, I learned it as -3. So I've been using it ever since. Okay, so this is definitely not balanced. We have a +1 against a -3. So that means we need 3 pluses to balance the -3. So the formula is going to be Na3PO4, sodium phosphate. This is a common cleaning compound. It's very alkaline. Okay, so let's do some more here. Now this is going to be a tricky one. Let's write the formula for aluminum sulfate. Okay, aluminum is Al, sulfate is SO4. We already looked up SO4 sulfate, and that's -2. Aluminum is going to be +3. Where is aluminum? Where is it? +3, right at the very top. Okay, so aluminum is +3, and sulfate is a -2. Now we have this conundrum again of 2s and 3s. Whenever we have a 2 and a 3 issue, we always think of a common denominator, which is going to be 6. So how many 3s are in 6? 2. How many 2s are in 6? 3. So this is a +6, -6, balanced. Now, sometimes they'll ask for the name. And if the name, like we talked about iron and copper having different forms, you've got to name it with the Roman numeral. For example, if I had copper sulfate, write the formula for that. Well, we know sulfate is a -2. That forces the copper to be a +2. So really, this is not copper sulfate, it's copper 2 sulfate. Um, let's see. Think of some more here. Now, that sheet I gave you, the common ion sheet, that's the common ion sheet. That means there are more ions than are on that sheet. These are the most common ones you run into. So, for example, let me just double check one thing here. I'm going to give you an example of vanadium. Notice the vanadium is available in charges of 2, 3, and 4. It can go up to 6 or even 7. So if I had, but I also gave you the formula. What would the charge be on that vanadium? Well, we know sulfate is a -2. So 3 times -2 is a -6. So that forces that vanadium to be a +6. Vanadium 6 sulfate. Still have one vanadium because we only have one. That one has got to balance the -6. Okay, is this starting to click a little bit?
Yes, but the vanadium one was kind of confusing.
I'm sorry, say again.
Everything else was it was easy to understand except the vanadium one since you said how did you get the 6?
Well, there's only one vanadium and it's balancing 3 sulfates. Each sulfate is a -2, and there are 3 of them, so that makes it -6. So that one vanadium has to balance a -6. That forces it to be a +6. That makes sense? Does that mean, since you're not saying anything, does that mean it's okay? You understand?
Uh, uh, Again, I'm gonna go back and rewatch this slowly and try to follow you, but I see. So, how are you determining that the vanadium is -6? I guess maybe I'm missing that. Or
Because each SO4
mm-hmm.
is a -2,
Okay.
and you have 3 of them.
Right.
So 3 times -2 is -6.
Just okay. So just based on the math on the right side is whatever is determined to the left is what determines the vanadium.
Yeah, they've got
Okay.
a well, the charges have to match. So in this case, I didn't give you which vanadium because we know from the common ion chart there are at least 3 versions. So which one do we use? Well, there's one that's not common, and that's +6 version.
Okay. Gotcha. Okay. Now that makes sense now. Okay.
A lot of people, after they start doing the ionic nomenclature, they like the molecular nomenclature better. It's much more straightforward. Okay, now a little thing on the different Dry Lab 5. It's much clearer than the one that's in your lab packet. Your lab packet has a whole bunch of pages and pages and pages of explanation. And basically, it's what I gave you are just practice problems. Now you can work on that tomorrow in after lecture, like we did last week. In fact, there are 2 dry labs this week. Next week there are 2 wet labs, but this week is all dry labs. So that seemed to work out pretty well, staying in lecture hall instead of splitting everyone up and all over we just stay there. And same with the rest of the week. Okay, well, that's what I wanted to cover on nomenclature. Now, there's also a naming convention for acids and bases. And I'm not going to touch that until we get to the subunit on acids and bases. So in the work, the dry lab that I gave you, if you see the word acid, don't do that one. Or AKU, AQ. That stands for aqueous. Those are also acids. So just cross those off. And there's probably 20 of them to cross off. Okay. I'm going to go into the next part of this lecture. If there are no more questions on this. I know you've never seen this before, so until you start working it, you're not going to have any questions. That's what's nice about dry labs. You get to practice it while I'm there. You can also do it at home if you want. Encourage you, you've been naturally getting into groups, which is very good. There's a ton of research out there that shows that students are in study groups, their achievement level is higher. And this is a number of research studies. So I highly encourage you to work with other people. And there's a nice set of groups that are starting to develop in the class. And I'm very pleased about that. If you're working by yourself and you're shy, I understand you not wanting to join a group, but it'll help you in the long run. Okay, so I'm going to go ahead and go on. All right, so what we're going to cover now, I'm going to get back to stoichiometry. And these problems are called limiting reactant problems. Now, last week I gave you the analogy of the bicycles. We had 10 frames, 10 wheels. How many bicycles can we make? Well, each frame needs 2 wheels.
Hi.
Yeah. And each frame needs 2 wheels. So that means if we're just looking at frames, we're going to need 20 wheels. If we're just looking at the wheels, since there are 2 wheels per frame, that means we can make 5 bikes. And we have 5 wheels in excess. So what limited the amount of bikes production? The number of wheels.
Isn't it 5 frames in excess?
I'm sorry, say again?
Is it 5 wheels or 5 frames in excess?
5 wheels. Excuse me. You are so right.
Right.
Yes, 5 frames. I prove once again I'm human. I do that every day. Okay, 5 frames in excess. Okay, so the wheels is the limiting reactant. This is an excess. So in your mind, you did a calculation for wheels and you did a calculation with frames, and you found that the frames produce too many bicycles. You didn't have enough wheels to go around. But with wheels, the wheels are totally consumed. So the limiting reaction is totally totally consumed. The number of frames, there's excess. So we're going to be doing this with chemicals now. You're going to have two givens now instead of one. One of them is going to limit the amount of water. The other is going to be in excess. So which one is it? That requires 4 calculations. Now you're going to get a take-home problem very shortly. That's going to be involving limiting reactants problems. I'm going to give you days to do it. Okay, so the first one is, let's just start with methane. See, that's CH4. Okay, so we're starting with 12.3 grams of methane. And we want to produce water. So if we start with 12.3 grams of methane, how much water do we make? Okay, remember this is a 3-step deal like last week. First thing is convert to moles. Now methane is, we have carbon at 1201. We have 4 hydrogens at 101 apiece, so that's 404. So 1605. That'll convert the methane, the grams of methane to moles because the grams cancel. Now we need to convert over to water because you know the moles of methane, based on our balanced equation up here, the ratio of methane to water is 1 to 2. So this is from the balanced equation, and this is why we balance it. So methane cancels. So we're left with moles of water. Now we need to go from moles of water to grams of water. So that means moles have got to cancel. And water is 1602 grams. So we have 2 hydrogens, 1 oxygen. 2 hydrogens are 101 apiece. Oxygen is 16. So that's 1802, not 1602. All right. So now we're going to get my calculator out. Calculator out. Okay, so that's 20 and 3 sig figs across. So we're looking at 27 6 grams of water. Okay, so that's if we used up all the methane. Let's see what happens when we use up all of the oxygen gas. It's going to be a similar calculation when we're starting with oxygen rather than methane. So this is going to be oxygen gas. And it's 23.4. Okay, oxygen is 16 for each one exactly. So that's 32 grams, 1 mole. This gets our grams canceling. Now we need to go from oxygen to water. And our balanced equation, the coefficients show 2 to 2. We're looking at the coefficients now. 2 to 2. Excuse me. The oxygens cancel. We're left with moles of water. And then water is 1802. Okay, so this will tell us how much water is produced with just oxygen. Okay, so notice the differences here. 27, if we just use methane, 13 with oxygen. So what limits the amount of water do we make? The methane or the oxygen?
Oxygen.
Exactly, because it produces less. There's not enough oxygen to go around, so it's totally consumed. So oxygen is our limiting reactant. Because it produced less product. Less product is what limits the reaction. Now we have excess methane. How do we find that? Okay, so we're going to start with oxygen. This is the third calculation. And we want to see how much methane is consumed. So we're going to do the same sort of calculation. This will get us moles of oxygen. We need oxygen on the bottom, methane on top, and it's a 2 to 1 from the coefficients from the balanced equation.
Professor Ferguson,
Yeah,
I have a question. I'm maybe not understanding this part. You know how you use 16.05 for methane to convert it to moles?
yeah,
But isn't methane a gas and oxygen's a gas? But then for oxygen you put 32. Why do you put 32?
because each oxygen molar mass is 16. 2 16s is 32.
Oh, I see. Wait, so you have to change how much? Like, what if it's like Avogadro's number or something, and there was like two of them? You have to like double it. I thought you always just put that factor in there.
Um, Now, when we're doing molar mass now, we have to look at the formula, what it is, how many of each atom you need. The formula for oxygen gas is O2. That means there are 2 oxygen atoms in there. Each one, the molar mass for each one is 16, and there's 2 of them. That's why it's 32. For methane up above, that's 1605. Okay, with methane, there's 1 carbon over here, 1 carbon at 1201, 4 hydrogens at 101 apiece, so that makes it 404. Add those together at 1605 grams per mole.
Okay, I get it because this is molar mass, so it's specifically
Exactly.
about.
Yep.
Okay,
Yeah, exactly.
okay.
Yeah. Now the
I got
limiting reagent problems, I simplify them, if you can believe it, looking at all this, to grams. Another problem developing a cough. But you can use Avogadro's number, you can use liters of gas at STP, but I'm just doing grams. So this is a grams limiting reactant problem. Okay, well, let me finish this guy out here. All right, and then we have 16, 0.05 for methane. Okay, so our moles cancel, our oxygens cancel, it leaves us with grams of methane. So this is how much is consumed. We're going to have excess. Basically, we're going to have less than 12. We have 587. So only 587 grams are consumed. We started with 12 though. So how much is excess? That's the fourth calculation. Well, we started with 12.3. We used 587. So how much is, and then this is consumed. This is excess. So in every limiting reactant problem, I will ask you, what's the limiting reagent? And how much is in excess of the other? So we have, this is excess methane, because methane was not the limiting reagent. So the limiting reagent will be totally used up, and the other one is going to be in excess. Now, sometimes the problems go one step more, and they say if if 10 grams of water is actually produced, what's the yield? Okay, so we actually made 10. We were theoretically trying to make 13.2. So this would be our percent yield. All reactions always have a theoretical yield and an actual yield, and they're never the same. So we're looking at 31%. %31% yield. So this is sort of what your problem is going to look like, your take-home problem. That's why Thursday I gave you that extra worksheet to work on looking these kind of problems. Because this one's got, you count the yield, 5 parts to it. Now, if you took 400, Chem 400, in the second week, you'd be doing these a lot. In fact, probably the first, well, not counting summer, you'd be doing these quite a bit. And not as a take-home either. You'd be doing them on the test in class. So anyway, yours is going to be a take-home. You have plenty of time to do it. I'll post one of these very soon, hopefully if I get to it. And I'm starting to fade right now. Okay, so it's good that we have a video of this. I have other videos also. If you go to YouTube and look up limiting reactants on my channel, you'll see probably 8 or 9 videos doing this. Okay, so how do you guys feel about this? Now, this is going to be the most complicated problem you're going to see in this class. When we get into solutions, those can get tricky. Acids and bases can get tricky too, but this is probably the trickiest one.
Professor,
Yeah,
please, how did you have a 31%?
because I divided 10 by 13. Did I do that wrong? 10 divided by 13.
Times 300?
Yeah. Yeah, 31%. It's actually 31.1, but 31%. So limiting reactant problems always have at least 4 calculations. 3 up above, that determines limiting reactant. The one below determines how much is consumed, and the one that subtraction problem below that determines what the excess is. Okay,
And you said the video on YouTube was limiting reactions, right?
they're called limiting reactants or
Reactants. Okay.
limiting agents.
Okay.
Or in fact, some are even called limiting reactants. Limiting
Limiting.
reactants, limiting. There's a number of terms they use. It's all the same thing.
Okay, maybe I'll just look up limiting and they'll probably search from
Yeah,
that.
get to my channel though first. Because otherwise you're going to get 8 million hits on this.
Okay, okay, got it.
And it goes back quite a few years, so.
Professor,
Okay, so
my answer is 75%. I don't know if I need to look. My answer is 75%.
I'm having trouble hearing you. Could you speak up really loudly?
My answer is 75%.
Yeah. You're talking about the yield?
Yes.
Yeah, the yield is always percent.
The answer is not, my answer is not 31. I don't know why.
Well, let me do it on my end. Let's see, 10 divided by 13, 2. Well, lo and behold, I got a different answer too. Oh, yeah. I don't know how I got that number there, but it's wrong. It is 75.6. Is that what you got? Did you get 75.6?
Yes, Professor.
Good. Thank you for pointing that out. Okay, so I want to go over just a few more things regarding the where things are located. I don't need to record this anymore.